Assalamu alaikum. Hello dear students. Today we will start with our first lesson, Chapter 7 Vibrations and Waves Part 1. By the end of this chapter, you will be able to define periodic motion and identify its characteristics, to define a vibratory motion and identify its characteristics, to define wave and identify its characteristics, to classify waves according to their types and nature, to recognize the electromagnetic spectrum. Currently, we will deal with the first two objectives. Consider the following motions. What is the common behavior between them? They are periodic, which means that they repeat themselves successively and identically in equal intervals of time called period. So what are the characteristics of a periodic motion? Periodic motions are characterized by their period, symbolized or denoted by capital T, which is the time required for one cycle or one exact repetition to be completed. For example, the period of the motion of Earth around the Sun is approximately 365 days. The period of the rotation of Earth around itself is approximately equal to 24 hours. Now, let's consider the following motions. What is the common behavior between them? They are vibrating. Each one of them undergoes a vibratory motion, which is a regular to and fro motion about its rest position between two extreme positions. Take a quick look at each of the following motions. They are periodic and vibratory, whereas the motion of a satellite around Earth is periodic but not vibratory. Then it's important to note that every vibratory motion is periodic, whereas it is not necessarily for periodic motions to be a vibratory one. The following objects undergo a vibratory motion, and each vibratory motion is periodic. So, each vibratory motion is characterized by its period T. Let's observe now the following simulation to better understand the notion of a period. This experiment was done to identify the period of a vibratory motion. First, displace the pendulum at a certain angle, 30 degrees for example, then release it and observe. Notice that the pendulum oscillates around its rest position between two equidistant extreme positions. Now, repeat the same steps, but this time we need to record the time taken by one complete oscillation. We will use a stopwatch. The time of the first oscillation is 1.76 seconds. Continue to measure the time of the second oscillation. We obtain 1.72 seconds, which is very close, and this difference is due to experimental error. The time of the third oscillation is 1.66 seconds, which is also close for the previous values. Now we will measure the time needed or the time taken by 5 successive oscillations to be completed, and the obtained value is 8.57 seconds. Calculating the average, we obtain 1.714 seconds. Notice that the values are very close to each other. Now we will calculate the exact period using the period timer, and the value of the period is 1.7076 seconds. You should take care that this is the case of no damping in the absence of friction, since in the presence of friction, the oscillatory motion damps gradually until it finally stops due to friction. In this chapter, we are interested in undamping vibratory motions. Let's identify now the characteristics of a vibratory motion. We will start with the period denoted by T, which is the time required for one cycle to be completed. It is expressed in seconds in the SI unit. We can write that the period T is equal to the duration of time divided by the number of cycles or oscillations, and we can write it as delta T divided by N. Let's have a direct application on this idea. Consider a clock pendulum that performs 5 complete cycles in 6.2 seconds. You are asked to calculate the period of this motion. Notice that 5 corresponds to the number of cycles, and 6.2 seconds correspond to the duration of time taken by this number of cycles. Then using the previous formula, T is equal to delta T divided by M, which is equal to 6.2 seconds divided by 5 cycles, and this gives us 1.24 seconds per cycle. Another characteristic is the frequency of the vibratory motion, which is the number of cycles per unit of time. It is expressed in hertz in the SI unit, and each hertz is equivalent to a cycles per second. We can write that F is equal to the number of cycles divided by the duration of time, and it can be written as N divided by delta T. Let's now try to find a relation between T and F. We've taken in the previous slide that F is equal to N divided by delta T, but each cycle takes one period. So we can replace the number of cycles by one cycle, and the duration of time can be replaced by a period. So F and T are inversely proportional. Before we practice, let's recall together the most commonly used units for T and F. For T, each minute is equal to 60 seconds. Each hour is equal to 60 minutes is equal to 3,600 seconds. Each 1 millisecond is equal to 10 to the power minus 3 seconds. For F, each 1 kilohertz is equal to 10 to the power 3 hertz, and each 1 megahertz is equal to 10 to the power 6 hertz. Consider the following application. Bee wings perform 11,400 beats in a minute. You are asked to calculate their frequency. Referring to the question, you are given the number of beats or cycles and the duration of time, which is 1 minute. Before I solve the application, you can pause the video and try to solve it by yourself. Then, we first need to start with converting the duration of time into the SI unit, and this is done by multiplying the time by 60, which gives us 60 seconds. Now we can use the formula F is equal to N divided by delta T, and the frequency of this motion is 190 Hz. In the second part, you are asked to deduce the period of the wings motion. Since you are asked to deduce, then you need to refer back to the answers obtained in the previous part. In this case, you are obligated to use the formula T is equal to 1 over F, and the period of this motion is equal to 0.005 seconds. Now, let's quickly list the main characteristics of a vibratory motion. A vibratory motion is characterized by its period, which is the duration of one oscillation, its frequency, which is the number of oscillations per second, and its amplitude. The amplitude A is the maximum displacement from the equilibrium position, and this is the equilibrium position, and this is the amplitude, which is the maximum displacement from the equilibrium position. Note that the amplitude A can be expressed as a distance or as an angle according to the studied system. In this case, it is expressed as a distance, and in this case, it is expressed as an angle. Let's have another application. A mass suspended from a spring describes a line segment of an average length L equal to 20 centimeter and makes 40 oscillations in 20 seconds. You are asked to find the amplitude, the frequency, and the period of the motion of this mass. Also, you can pause the video and try to solve the application by yourself. First, the amplitude A is the half of the length of the line segment L. This is the amplitude, which is half the length of L. Then dividing it 20 by 2, we obtain A is equal to 10 centimeter. To calculate the frequency, we have the number of cycles and the duration of time. So we can simply use F is equal to N divided by delta T, which gives us 2 Hz. And finally, we can calculate the period by dividing 1 divided by F, which gives us 0.5 seconds. Let's summarize now what was shown in this video. A periodic motion is the motion that repeats itself identically and successively in equal intervals of time. It is characterized by its period t, which is equal to delta t divided by n, and its frequency f, which is equal to n divided by delta t. Also, a vibratory motion is a regular to and fro motion around a rest position between two extreme positions. It is characterized by its period t, its frequency f, and don't forget that f is equal to 1 divided by t, and also it is characterized by its amplitude a. Thanks for your attention.